Section 1.3, the language of functions and relations. So let's start with a relation. So we're going to say a relation R from set A to set B is going to be a subset of that A cross B. And this means if we have that ordered pair x comma y, we're in that cross. We say that x is related to y by R. We can also write it as x capital RY. And that is only the case if x comma y is in R. We say that first set A is domain, and that second set B, we're going to use the term codomain rather than the more familiar range. So again, if you see x, r, y, that means x comma y is in this relation R. And again, if we've got that little slash through it, it means that it is not the case. So let's see some examples. A is 1, 2, B is 1, 2, and 3. And we are defining this relation R from A to B as follows. So x comma y is in R means that x minus y all over 2 is an integer. So let's state what ordered pairs are in that cross A cross B, and then which are in R. So down here I've got the full cross 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, and 2, 3. So basically I'm going to try each one of those ordered pairs in this relation and see which one of them works. So if we do 1, 1, I get an integer out, so I will say that is in R. However, if I try 1, 2, I get a fraction. That is not an integer. I want an integer, that was in my problem, so I would say that is not in R. So similarly, 1, 3 is in R, 2, 1 is not in R, 2, 2 is in R, and 2, 3 is not in R. So R was 1, 1, 1, 3, and 2, 2. And then let's just familiarize ourselves with that notation. So is 1 R3, is 2 R3, is 2 R2. So again, remember what that means is 1, 3 would have to be in R for 1 R3. And as we can see, it is, so I'd say yes. 2, 3 is not in R, so I've got a little slash when I tried to write 2 R3. And again, 2, 2 is in R, so we'll say yes for that one. And then finally, what is the domain and codomain of R? So again, the domain is the first set A, and the codomain, again, we're not using that term range, is the second set B. Let's look at another relation, specifically the circle. So we've got the real numbers as both of our two sets there. So we've got real cross real. And our relation means that we've got x squared plus y squared is 1. All right, well, let's take a couple of numbers here and see if they work. Let's start with 1, 0. Is that in this relation C? Well, if I plug it in my equation, 1 squared plus 0 squared equals 1 is a true statement. So we'll say yes. How about 0, 0? Similarly, I'm going to plug it in my equation. That one does not work, so I would say no. We can put in this third pair with a radical. And again, might take a few more steps to simplify that. But if we do that, that is a true relation, so I would say yes for that one. Again, our next few, we've got that notation. So is -2C 0? Again, that means is -2, 0 in C. And again, if I throw those numbers in, this time it is not a true statement, so I say no. Similarly, is 0C -1? That one does work out, so yes. And finally is 1C1. Again, I plug it in. That one does not work, so I would say no for that. So again, anytime we've got a number, we'll just plug it in, whatever this relation is, and see if it works out. All right, what is the domain and codomain? Again, those are both going to be the set of all real numbers. And then finally, let's draw a graph for that by plotting that in the Cartesian plane. And we're going to have a circle here. You'll notice we've got radius of 1, because we were given that radius of 1 as part of our problem. All right, let's talk about arrow diagrams. You've probably seen these before, but you may never have actually done anything with them. So basically the arrow tells us how the relation works. So we'll draw an arrow from x to y if x are y. So let's see what that's going to look like. So here I've got A is 1, 2, 3, B is 1, 2, 5, and we're going to look at two relations. Let's start with S. So S means that x is less than y. So let's look down here at x. So I'm going to take 1 to 3 and 5. I didn't take it to 1 because 1 is not less than 1. 2, I'm going to draw from 2 to 5, and 3 I'm going to draw to just 5, because that is when that statement is true. Now T, you'll notice I do just have ordered pairs, so I've got 2, 1 and 2, 5. So I drew 2 to 1, and I also drew 2 to 5. As we can see, you can have several arrows going from the same number. You can have several arrows going to the same number. As far as if we're just in a relation, we can pretty much have as many arrows as we want. All right, so that's the relation. Let's look at functions. So our nice formal definition, a function f from set A to set B, it is a very specific relation. And again, the domain is A, the codomain is B, but we have two things that have to be true. So for every element in x in A, there is an element y in B, such that x, y is in F. And then for all elements x in A and y and z in B, so I'm looking at 2 there, if x, y is in F and x, z is in F, then y equals z. You might have heard the less formal definition of a function in previous math classes, which is basically that you can't have repeated x's. And this is essentially a very formal way of saying that exact same thing. So again, our less formal ways of describing that, every element of the first set A is the first element of that ordered pair, and then no two distinct ordered pairs in F have the same first element or x value. And again, we've got that function notation, which we are hopefully familiar with. All right, let's look at an example. Here I've got A is 2, 4, 6, B is 1, 3, 5, and we're going to have three relations, and which of them are functions? So relation R is 2, 5, 4, 1, 4, 3, and 6, 5. So we could draw this diagram here on the bottom if it helps to see it. You'll notice 4, we've got 2 arrows coming out of it. That is not okay. Now it's okay to have 2 arrows going to the same point, as they are here for 5, but we cannot have 2 arrows coming out of the same value. So this repeated 4, that's why R is not a function. All right, my next one, for every x, y in that cross, A cross B, x, y is in S, means that y equals x plus 1. Is that a function? And here we are going to say no, because it's not true that every element of A is the first element. So 6 is in A, but there is no y in B such that y equals 7. So basically, I was not able to use this 6 value. We didn't concern ourselves with that in our earlier math classes, but this more formal definition means that I can't have this missing value. Finally, T, we've got this lovely diagram here, and let's see if that one works. So here we will say it is true. As you can see, every element of T has just the one arrow, so they're all used once. You'll notice I skipped the 3 in B and used the 1 twice, but that is okay. And again, here is our written definition. The last thing we'd like to talk about here are function machines. You may have seen these before, and this is a way of just representing visually some function is happening. We don't necessarily know what it is. We're going to input this x value. Again, something happens to it, and the output is that function value f of x. So let's look at the squaring function. Here, again, we're in the real numbers, and we would say f of x equals x squared. And again, we could try to describe that with different symbols. Next, we've got a function you may not know. It's called the successor function. Note for this one, we are only in the integers. And we're going to define this as g of n is n plus 1. So basically, it's the next integer, which is why we call it the successor. And again, there's a couple ways we can describe it. And you'll sometimes see this notation. I've got the z colon n arrow n plus 1. So again, g is the function. N is what I'm putting in, and n plus 1 is what I'm getting out. We've also got the constant function. Now here I'm defining this from the rationals to the integers. You'll notice my formula h of r equals 2. In other words, I'm going to get 2 out no matter what I put into it. And that's why I have integer here, because of course 2 is an integer. And again, you can see that notation h colon r arrow 3. So again, h is the function name, r is what I put into it, and 2 is what I get out of it. And here are the squaring function, successor function, and constant function with those pictures of functions with them. Again, we've got lots of functions. There's lots of ways we can describe them. Let's look at a relation is a subset of a Cartesian product, and a function is a special kind of relation. So again, every function is a relation. And again, here's the nice formal way. So f, we can define as x comma y, is in that cross, a cross b, where y equals f of x. And we have something very similar there for g. When are they equal? F equals g, which we write like that. It's true if and only if the function values are the same for every single x value. So if even one of them doesn't work, it is not equal. So let's look at these two functions. F of x is the absolute value, and g of x is the square root of x squared. Do those two things actually equal each other? We would say yes. Every single number we put in there, every single real number, we will get the same value out. So we will say that yes, those two functions are equal to each other. And that is everything in section 1.3.